Hi. In this session, we're going to cover a nice review problem that will look at how to infer one random variable based on another. And in this problem, we're given two random variables, x and y, and we're also given their joint PDF, which we're told is a constant 2/3 within the region bounded by these orange lines, and outside of that region, the joint PDF is 0. So the first thing we're going to look at, or the first thing that we're asked to do, is find the LMS estimator of y based on x. Now remember that the LMS estimator is really just a conditional expectation. So the LMS estimator of y based on x is the conditional expectation of y given x. Now, when we have a plot of the joint PDF and we're dealing with these two random variables, it's often, and especially when the joint PDF is constant like this, it's often easy to calculate this conditional expectation visually. So what we really need to do is just say, given any particular value of x, what is the expectation, the conditional expectation of y? So what we can do is we can just pick some values of x and see visually what that conditional expectation is. So for example, if x is a half, given that x is a half, and since this whole joint PDF is uniform, then this slice, the conditional slice of y, will be from here to here. And that slice, the conditional distribution of y, given that x is a half, will also be uniform. So it'll be uniform from here to here. And if it's uniform, we know that the conditional expectation will just be the midpoint here. And so that would be what the conditional expectation of y would be, given that x is a half. And we're doing the same thing for x equals 1. And we'll see that, again, because everything is uniform, this slice is also going to be uniform. And so the conditional expectation will again be the midpoint, which is there. And then if we just look at it, within this region, it's always going to be the midpoint. And so we get that the conditional expectation of y given x will just look like that line, which you can think of it as just bisecting this angle formed by these two parts of the region. But things are a little bit different, though, when we move to the region where x is between 1 and 2. Where between 1 and 2, say at 1.5, this line doesn't continue because now the slice of y goes from here to here. And again, it's still uniform. So the conditional expectation will be the midpoint, will be there. And similarly for x equals 2, it would be here. And so for x between 1 and 2, the conditional expectation actually looks like this. So you see that there's two linear parts of it, but there's a kink at x equals 1. And so that, by looking at this visually and taking advantage of the fact that everything is uniform, we can pretty easily figure out what this conditional expectation is. So now let's actually just write it out algebraically. So for x between 0 and 1, we said that it's this line, which if we look at it, that's just 1/2 of x. Now this is for x between 0 and 1. And if x is between 1 and 2, it's going to be this line, which is a slope of 1. And if we extend this down, it hits the y-axis at -1/2. So it's x minus 1/2 if x is between 1 and 2. And otherwise, it's undefined. So we'll focus on these two cases here. The second part of the question, now that we have this, now that we know what the LMS estimator is, we're asked to find what is the conditional mean squared error of this estimator. So we want to know how good is it. And one way of capturing that is to look at the mean squared error. And so recall that the mean squared error, or the conditional mean squared error, is given by this expression. So what we're saying is this is what we estimate y to be. This is what y really is. So this difference is how wrong, or the error in our estimate. We square it, because otherwise positive and negative errors might cancel each other out, so we square it. And then this is for the case we're just looking at each individual value of x for now. So this is why it's conditional mean squared error. So how do we calculate this? Well, remember that this g of x, right, we said the LMS estimator is just a conditional expectation. So it's just expectation of y given x. Well, then if you look at this, what this reminds you of, it reminds you of the definition of what a conditional variance is, right? Variance is just you take the random variable, subtract its mean, square it, and take the expectation of that. This is no different, except that everything is now in the conditional world of x. So this is actually the conditional variance of y given x is little x. Now, what is conditional variance of y given that x is little x? Now, we can, again, go back to this plot to try to help us out. We can split this up into regions again. So just take some little x as an example and see what the variance is. So if little x is a half, then y, we know that the conditional distribution of y would be uniform, we said, from 0 up to here. Well, that point is from 0 to 1/2. And remember, the variance of a uniform distribution is just the width of the uniform distribution squared divided by 12. And so in this case, the width would be 1/2 squared over 12. And in general, for the region of x between 0 and 1, the width of the conditional distribution of y will always be x, because the width will go from 0 to wherever x is. So because of that, the conditional variance will just be x squared, the width squared, over 12 when x is between 0 and 1. Now let's think about the other case where x is between 1 and 2. Well, if x is between 1 and 2, we're over here. And now if we take the conditional distribution of y, it's again uniform. But the width now, instead of varying with y, it's always going to be the same width. Right? Each of these slices have the same width. And the width is always, it goes from here, this is x minus 1, and that's x. So the width is always going to be a constant 1. And so this variance is going to be 1 over 12. And from that, we get our answer for the conditional mean squared error. Now, part C asks us to find the mean squared error, which is given by this expression. And we'll see that it looks very similar to this, which was conditional mean squared error. And now, given what we know from part B, this is easy to calculate. We can just apply total expectation, because this is just equal to the integral of the conditional mean squared error, and then we need to also multiply this by the PDF of x, and then integrate over x. And that integral should be from x equals 0 to 2, because that's the only range where x is, that applies for x, given this joint PDF. Now, in order to do this first, though, we need to figure out what the joint PDF of, what the PDF of x is. And in order to do that, we can go back to our original joint PDF of x and y and marginalize it. So marginalizing just means you can think of it as taking this joint PDF and collapsing it onto the x-axis, so that you take everything and integrate out y. Now, to do that, let's do that up here. We can split it up into two sections. So the section of x between 0 and 1, we integrate the joint PDF from y equals 0 to y equals x, which is this portion of this line. So we integrate y. The joint PDF is 2/3, and we integrate that from y. We integrate y out from y equals 0 to x. And then for the portion of x from 1 to 2, we again integrate y out. But now we integrate y from x minus 1 up to x. So this is x between 0 and 1, and this is x between 1 and 2. So we just do some little bit of calculus, and we get that this is going to be 2/3 x when x is between 0 and 1, and it's going to be 2/3 when x is between 1 and 2. So now that we have what the marginal PDF of x is, we can plug that into this and plug in what we had for b, and then calculate what this actually is. So remember, we need to take care of these two cases. There's two regions, x between 0 and 1 and x between 1 and 2. So the conditional mean squared error for x between 0 and 1 is x squared over 2. So between 0 and 1, this first part is x squared over 12. The PDF of x in that same region is 2/3 x. And we integrate that in the region from x equals 0 to 1. And then we also have the second region, which is x from 1 to 2. In that region, the conditional mean squared error from part b is 1/12. The marginal PDF of x is 2/3. And we do this integral. And if you just carry out some calculus here, you'll get that the final answer is equal to 5/72. Now, the last part of this question asks us, is this mean squared error the same thing? Does it equal the expectation of the conditional variance? And it turns out that yes, it does. And to see that, we can just take this and use the law of iterated expectations, because iterated expectations tells us that this is in fact equal to the expectation of y minus g of x squared given x. That's just applying law of iterated expectations. And then if we look at this part that's inside is exactly equal to the conditional variance of y given x. And so these two are in fact the same. In part C, we calculated what the marginal PDF of x is, and it'll actually be used later on in this problem. So for future reference, let's just write it down here in this corner. Now, so far in this problem, we've looked at the LMS estimator. And of course, there are other estimators that you can use as well. And now in part D, let's look at the linear LMS estimator. Now remember, the linear LMS estimator is special because it forces the estimator to have a linear relationship. So the estimator is going to be a linear function of x. Now compare that to what the LMS estimator was in this case. See, it was two linear pieces, but there was a kink. And so the entire estimator wasn't actually linear in x. Now the LLMS estimator, the linear LMS estimator, will give us a linear estimator. It's going to be a linear function of x. And we know that we have a formula for this. It's the expectation of y plus the covariance of x and y over the variance of x times x minus expectation of x. All right, so in order to calculate what this is, we just need to calculate what four things are. Now let's start with this last one, the expected value of x. Now to calculate the expected value of x, we just use a formula. And from before, we know what the PDF of x is. And so we know that this is just going to be x times fx of x dx. And in particular, this will give us that this is equal to, from 0 to 1, it's going to be x times the PDF of x is 2/3 x. So it's 2/3 x squared. And from 1 to 2, it's going to be x times the PDF of x, which is just 2/3. So it's 2/3 x dx. And when you calculate this out, you'll get that it is equal to 11/9. Now, let's calculate the variance of x next. In order to calculate that, let's use the formula that the variance is equal to the expectation of x squared minus the expectation of x quantity squared. We already had the expectation of x, so let's calculate what the expectation of x squared is. Now, it's the same idea. Instead, we have x squared times fx of x dx. And we'll get the same sort of formula. We'll split it up again into two different parts. From x equals 0 to x equals 1, it's going to be x squared times PDF. So it's 2/3 x cubed dx. And then from x equals 1 to 2, it's going to be x squared times 2/3. So it's 2/3 x squared dx. And when we calculate this out, we'll get that it's equal to 31/18. And from that, we know that the variance is going to be equal to expectation of x squared minus expectation of x quantity squared. Now, expectation of x squared is 11/9. Expectation of x squared is 31/18. Expectation of x is 11/9. And when we calculate this, we get that the variance is equal to 37/162. All right. So now we have this and we have that. Let's calculate what expectation of y is. Expectation of y, let's calculate it using the law of iterated expectations. Its law of iterated expectations tells us that this is equal to expectation of the expectation of y conditioned on x. Now, we already know what expectation of y conditioned on x is. That was the LMS estimator that we calculated earlier. It's this. All right, so now we just need to calculate this out, and we can do that. So we know that in the range from x between 0 and 1, it's equal to 1/2 x. So in the range from 0 to 1, it's equal to 1/2 x. But then we have to use total expectation, so we have to multiply by the PDF of x in that region, which is 2/3 x dx. And then in the range from x equals 1 to 2, this conditional expectation is x minus 1/2. And the PDF of x in that region is 2/3. Okay. Now, when we calculate out this value, we'll get that it's equal to 7/9. And now for the last piece is the covariance of x and y. Now remember, the covariance, we can calculate that as the expectation of x times y minus the expectation of x times the expectation of y. We already know the expectation of x and the expectation of y, so we just need to calculate the expectation of x times y, the product of the two. And for that, we'll use the definition, and we'll use the joint PDF that we have. So this is it's going to be a double integral of x times y times the joint PDF. And the tricky part here is just figuring out how to actually, what these limits are. So first we'll integrate in this order, x and y. Now, let's split this up. So let's focus on splitting x up. So for x between 0 and 1, we just need to figure out what are the values of, what's the right range of y to integrate over such that this is actually non-zero. Because remember, the joint PDF is easy. It's just a constant 2/3, but it's only a constant 2/3 within this region. So the difficult part is just figuring out what the limits are in order to specify that region. So for x between 0 and 1, y has to be between 0 and x, because this line is y equals x. Right? So we need to integrate this from 0 to x, x times y times the joint PDF, which was 2/3. And now let's do the other part, which is x from 1 to 2. Well, if x is from 1 to 2, in order to fall into this region, y has to be between x minus 1 and x. So we integrate y from x minus 1 to x. Again, it's x times y times the joint PDF, which is 2/3. All right. And now, once we have this set up, the rest of it, we can just do some calculus. And what we find is that the final answer is equal to 41 over 36. Now, what that tells us is that the covariance of x and y, which is just expectation of x times y, the product, minus expectation of x times expectation of y. We know expectation of x times y now, it's 41 over 36. Expectation of x is 11 over 9. Expectation of y is 7 over 9. So when we substitute all that in, we get that this covariance is 61 over 324. All right, so now we have everything that we need. Expectation of y is here. Covariance is here. Variance of x is here. And expectation of x is here. So let's substitute that in. And we can figure out what the actual LMS estimator is. So expectation of y, we know, is 7 over 9. Expectation of x is 11 over 9. And when you divide the covariance, which is 61 over 324, by the variance, which is 37 over 162, we'll get 61 over 74. And so that is the LMS estimator that we calculate. And notice that it is, in fact, linear in x. So let's plot that and see what it looks like. So it's going to be a line, and it's going to look like this. So at x equals 2, it's actually a little bit below 1.5, which is what the LMS estimator would be. At x equals 1, it's actually a little bit above 1/2, which is what the LMS estimator would be. And then it crosses 0 at around roughly a quarter. And it drops actually below 0. So if we connect the dots, it's going to look something like this. So notice that it's actually not too far away from the LMS estimator, but it doesn't have the kink because it is a line. And note also that it actually drops below. So when x is very small, you actually estimate negative values of y, which is actually impossible given the joint PDF distribution that we're given. And that is sometimes a feature or artifact of the linear LMS estimator, that you'll get values that don't necessarily seem to make sense. So now that we've calculated the linear LMS estimator in part D, which is this, and the LMS estimator in part A, which is this, we've also compared them visually. The linear LMS estimator is the one in pink, the straight line, and the LMS estimator is the one in black with the kink. It's an interesting question to now ask, which one of these is better? And in order to judge that, we need to come up with some sort of criterion to compare the two with. And the one that we're going to look at in part E is the mean squared error. Which one gives the lower mean squared error? And so specifically, we're going to ask ourselves, which of these two estimators gives us the smaller mean squared error? Is it the linear LMS estimator given by L of x, or is it the LMS estimator given by g of x. And now we know that the LMS estimator is the one that actually minimizes this. The LMS estimator is designed to minimize the mean squared error. And so we know that given any estimator of x, this one will have the smallest mean squared error. And so the linear LMS estimator, its mean squared error has to be at least as large as the LMS estimators. All right. And the last part of the question now asks us to look at a third type of estimator, which is the MAP estimator. Now we want to ask, why is it that we haven't been using the MAP estimator in this problem? Well, remember what the MAP estimator does. In this case, what we would do is it would take the conditional distribution of y given any value of x, and then it would pick the value of y that gives the highest value in the conditional distribution. And that would be the MAP estimate of y. But the problem in this case is that if you take any slice here, so condition on any value of x, any of these slices, if we just take this out and look at it, it's going to be uniform. This is the conditional, this is what the conditional distribution of y given x is. It's going to be uniform between 0 and x. Now what the MAP rule tells us is, well, we're going to pick the value of y that gives us the highest point in this conditional distribution. You can think of it as a posterior distribution. Now, what's the problem here? Well, every single point gives us exactly the same value for this conditional distribution. And so there's no unique MAP rule. Every single value of y has just the same conditional distribution. So there's no sensible way of choosing a value based on the MAP rule in this case. But compare that with the LMS estimator, which is just conditional distribution, conditional expectation. In that case, we can always find a conditional expectation. In this case, the conditional expectation is the midpoint, which is x over 2, just as we had found in part A. Okay, so in this problem, we reviewed a bunch of different ideas in terms of inference, and we took a joint PDF of x and y, and we used that to calculate the LMS estimator, the linear LMS estimator. We compared the two, and then we also looked at why, in this case, the MAP estimator doesn't really make sense. All right, so I hope that was helpful, and we'll see you the next time.